So in this video, I will just walk you through the idea of sample size and the idea of power of a study. And really it's an introduction to those concepts and also the calculations that are applied to them, and a couple of kind of heuristics to kind of, get you going with some of these things. So the reason that we bother with sample size is really to identify how many people we should study, because typically we can't study everyone that's present. For example, it's unlikely you'll ever be able to study all of the babies born in Ireland, though there is a study in the UK that has been going on where they did study every baby born in a particular week back in the 50s, but that's extremely rare. So usually what you're doing is studying a small selection or a sample of that overall population, and then the results you draw from that can be inferred to the larger population. So that's this idea of inferring findings about a population in general. So one of the easiest ways to think about it is to think about the political polls that you read about in the newspapers. They often will give you a projected result, and they'll say that there's a margin of error of a certain number of percent, and that margin of error is actually then relevant for the predictions that you can make based on that data. And that's the same idea, except we are studying a selection of the overall population. Okay, and you will have a difference between what you get in a poll pre-election and then the result of the election. The same way you will have a difference between what you get if you do a study of a small percentage of the overall population and then with the overall population at the end of it. Now, there is a very simple reason to actually limit the number of samples that you do, and that's just practicalities in many cases. It may be too expensive and may take too long. If you want to get, do a glucose measurement on everybody in the country, that would be possibly unachievable to do directly. There might be ethical reasons. If you're giving people a drug or a new therapy or a new treatment, then you're better off not doing it on everyone just because, when you don't know if it's going to be any better than the old treatment. So you want to identify what's the minimum number of people that you can actually investigate to get a good and robust answer. So the idea of just enough, and you've probably heard of just in time, but really you're looking at just enough participants to be involved in any study. So I think the concepts underpinning sample size are fairly straightforward. Now, picking the sample size is difficult. You can do calculations to try and figure out how many might be required, but there is a bit of a black art to it. There are even a couple of publications which say that the best guess estimate of an experienced researcher in the area is actually pretty close to what you'd get if you go through the long and formal statistical process, given the errors that are inherent in both of those. Power is a little bit more difficult to understand, but I think you all have an intuitive understanding of it already. You just don't know it in this context. And power really is the ability to make sure you get the right answer. So what's the likelihood you get the right answer when you do a study? And if you think about that from a test point of view, what I'm talking about are false negatives and false positives. Okay, so that's really what it boils down to. So whenever we do a study, we want to make sure that we have a low likelihood of errors. Okay, and that means that if we're doing it well, and we're not likely to make mistakes doing it. You can have an error where you actually identify a difference when in actuality nothing really exists. So that's like finding an effect of a drug or a treatment where no actual effect of that drug or treatment exists in the real world. It's just a statistical fluke based on your study population or your study design. All right? And that often is, a result of having small numbers of samples. And that's considered to be a type 1 error. All right? Now, the false negatives is when there actually is a difference, but you don't have enough people in your study population or enough samples in your study population to actually identify that difference that really is there. So you just can't find it. Okay? And that's a type 2 error. So to reiterate, type 1 is a false positive, type 2 is a false negative. So type 1, you find a difference that doesn't exist. Type 2, you don't find a difference even though there's one there. But if you think of it in the false positive and false negative way of thinking it, then that will actually help you because you're used to that type of language from a laboratory setting. Now, the power of a study then is worked out as 1 minus the likelihood of being a false negative. And the idea is that you are trying to get as close as possible to really identifying something that's there. So you don't want the false negative chance to be high because then your power will be low. So you want your false negative chance to be low, which means you have a higher power. It's never going to be perfect, but you want to get as close to that as possible. So there are a number of different influences on sample size. And you can see these highlighted in the different columns below. So if you decrease the minimum expected difference between two measurements, then you're going to have more samples. So if the difference between the healthy and the diseased patients is 10 grams per litre, okay, and the average measurement in the blood is 5 grams per litre, then it's going to be pretty obvious that the healthy controls will be 5, the diseased will be 15. So the expected difference is big. However, if the difference is only 0.1, then it becomes much more challenging to do with a small number, because the normal range and normal variation will mean that some people will have a high level and some people will have a low in both populations, so there will be overlap. So the minimum expected difference is also known as the effect size. And sometimes you could find that from the literature, sometimes you can find that from previous studies, sometimes it is that best educated guess I mentioned earlier. So based on your scientific knowledge, what do you think will be the minimum difference that you're going to expect between your two groups, your two treatments, whatever it happens to be? So the lower that is, the more samples you need. So you're kind of compensating for a smaller difference with a larger number of samples. If your standard deviation goes up, you will need to have more samples. So going back to that previous one I mentioned where it was 5 grams per litre and then 15 grams per litre in the diseased patients, if the standard deviation of those measurements is, let's say, 7.5 or 8, then immediately you can see it's 5 plus or minus 8, and then it's 15 plus or minus 8. So 5 plus 8 is 13, 15 minus 8 is 7. So those are two overlapping samples at the extreme of a 1SD. Now the example I've given you is a very, very extreme and crude example, but you get the idea of if you have these overlapping distributions of values between both groups, then you will have an issue. And again, the way you deal with that is you have more samples, okay, so that you're getting a truer measurement of the mean. So then coming into power, so if you have a higher power and an ability to, if your study has a higher power, or the intervention or the test has a higher power, then that means that you're less likely to pick up a false negative, i.e. you're really finding things that are there. And if you have a higher powered study, then you can actually reduce the number of samples you need because your study is basically better powered. And that means you're less likely to have a false negative, you're more likely to find that difference that actually exists there. The other one then is the p-value. So that's the significance threshold in any other parlance. Now we will come back and talk about p-values in the separate one where I talk about its p-value is not the king that you might believe it to be. But if you're aiming for a lower p-value, which avoids false positives, okay? So a lower p-value to avoid those false positives means that you're going to have more samples to get there, because if you go from a p-value of 0.05, that's a 5% chance you've just got the result as a fluke. If you want to go down to 0.01, so a 1% chance that you've got a fluke, then you will have to have more samples to do that. Simple as that. And then the last one, which is, I suppose, a little bit more difficult to get your head around in one way, but it's whether or not you're expecting each population to have average values and then a range of high and a range of low around the average. So that's tails in population distributions or histograms. So does it have one or two tails? So are you only comparing results that start off from a mean and get higher? Or are you comparing a set of results that goes from low to mean to high? So that has an impact on sample size. Typically a one-tailed comparison, which wouldn't really be advised in virtually any case, would require less samples, basically. You can use it, but you have to go into your experiment stating explicitly at the start, we are comparing these things on the basis that the increase is the only thing we're looking for. We don't expect a decrease to be found at all. That means you'll miss a decrease, but it also means that you're more linked, let's say, to just looking after that increase. So here's a couple of different populations. So in each of those pairs of panels, you can see two populations. You can see in A, you have two fairly symmetrical populations that are where the means are separated. So the mean is basically the highest point on the peak. So you can see that the means are separated reasonably well. So that means that and there's not a huge amount of spread either. So that means that those two populations are probably distinct. If you look at B, you have two populations that are overlapping and are possibly not distinct. And again, in C, you have these very spread out populations with long tails at the end of them. Okay, and that's something we'll come back to when we talk about kurtosis. But you can see again that that's overlapping. So of those three, A really has the highest power, as in that study is the best powered. So you'd believe that the top and the bottom panel in A are different, whereas you'd be hard pressed to prove that B is different. And C may be different, but you can also see that in panel C, you have an awful lot more samples. Okay, so that might be a higher population that needs a lot more people in it or samples in it, so that you can actually distinguish between the top and the bottom panel in C and distinguish between them accurately and sensibly. So we've mentioned this idea about what influences power, but just to recap quickly, it's increased by greater size of the effect. So if you look again in each of these, there's two sets of panels, and you can see the arrow is kind of pointing in the direction of what will increase the power. So in the top one, greater size of the effect, the further you go from the mean, the greater the power you're going to have. So if you go from healthy controls are 5 and diseased are 15, that's fine. But what if diseased are 50? Then you have a much bigger difference. So the effect size is greater, the expected difference is greater, so then you have a better powered study. Larger sample size tends to cause regression towards the mean, which means that it kind of, the middle column is going to increase and it squeezes the shape of the distribution until it's more normal. All right? And again, that means that it's more likely the two populations won't overlap significantly. Power is decreased by a high standard deviation because you're spreading out that population wider. And a high standard deviation means you'll eventually have populations that overlap each other, just like we saw in panel C in the previous one. And then it's also decreased by the significance level. So depending on what you want, like how sure, let's say, you want to be that that difference is genuine. So here's an example that we'll have a quick look at. So we're comparing cancer and Diet Coke. So does Diet Coke cause cancer? We have a control group who never touched Diet Coke, and we have an exposed group who are drinking it all the time. So you compare them and find that there's no statistically significant difference. So that means your p-value is greater than 0.05. Now, two things could happen with this. The first one is that the results that you find are absolutely genuine and true, so that you found a real result. The other one is that you've made a mistake. So you've made a false negative or a type 2 error mistake. You didn't see a difference that was really there. So there really is a difference. So Diet Coke actually is the thing that's doing the damage, but you can't actually see that. So if you design a well-powered study, it's more likely that you'll get the true results, and it's less likely that you'll get those false negative results. So that's really why it's important to consider these type of things in your study design. So if you want to kind of get a view about how standardized difference influences power, and the standardized difference is really the difference in your two means divided by the standard deviations, and it really just brings that standardized difference into one place and standardizes it for those populations. So in this table, which I've pilfered from a paper that I can't remember the reference from, the number of people needed is indicated by the expected standardized difference. So how many kind of standard deviations difference are you looking for? And then you can see if you're looking for a relatively small standardized difference of 0.3 and you want a power level of 0.8, which would be pretty normal, you're looking at quite a large number of participants. And then at the same time, if you were looking at a larger difference, you need less people because the difference is much bigger, and that means that you're more likely to spot that difference in a true manner than you would otherwise. There is a quick and dirty formula for doing this, okay? So for an alpha of 0.05 and for a beta of 0.2, like a power of 0.8 or 80%, you basically get a number of participants or number of samples. So that's what number means here. It's number of participants or samples. It's the number of 16 divided by the standardized difference squared. Okay? It's crude and dirty, but it's quick and it's close enough in many cases. You can go into it in slightly more detail using something like a nomogram or any of the vast number of calculators that you'll find online. There are bucket loads of them. You can even do this on your smartphone. Okay, so you pick your standardized difference in this case. So let's say standardized difference is 0.5, and let's say we want a power of 0.8, and then you can pick your significance level. So I want a significance of 0.01, and then I go up to here, and that tells me I'm looking at probably around 200 samples. If my standardized difference was lower, let's say if it's 0.25, with the same power and the same significance, I'm now looking at somewhere in the region of 500. Okay, so remember, I went from 500 from somewhere in the region of 200. Big difference there. Okay, and that's basically from the standardized difference. So when you're comparing two means, you can go in and figure out in a slightly more sophisticated way what your power is. So I've given you the link to the paper at the bottom, and for this type of comparison, you need the standard deviations of each group. You need to identify your Z critical and your Z power. I'll show you those on the next page. You have your minimum expected difference, okay? And basically, if you plug everything in, you'll get the total number that you need. So the total number is all of the participants or all of the samples, okay, both healthy and diseased. And then what you need to do is package all of those together, divide it by 2-ish, and you're left with the actual value that you want for each group that you need to recruit. So those Z crit and Z power, so for a desired P or a desired power, so let's just have a look at those quickly. So if you want a significance level of 0.01, then your Z crit is going to be 2.58, just about. And if you want a power of 0.8, it gives you a Z power equivalent of that. So they are kind of critical values for common ones. You can look all of these up in a table, and then you can get any value you want for anything ever. But really this is if you're comparing two means. Okay, so you can work through this, and you'll see that it's, the thing that you're basically dividing by is similar to what you had on Layer's formula, which was the quick and dirty one. And you will get a difference between them. So, take-home message. The more that your mean is from the mean specified in the null hypothesis, the higher the power. So that's basically, the more the difference in the two groups, the more the mean is different in the two groups, the higher your power. The higher significance level, the higher the power. Okay? The smaller the standard deviation, the higher the power, and the larger the sample, the higher the power. And of all of these, probably the last two are really key. More sample, less standard deviation is going to make a better part study.